Welcome, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. Today's episode I'm very excited about. This is peak derivative calculus. This is the top. This is the pinnacle of what we're doing with derivatives. It's not everyone's favorite section. It is widely believed by many students to be the most difficult section, or it's the section students make the most mistakes on tests and quizzes, in my experience. This is it. We're doing derivative story problems. Again, related rates was not good enough. We need to do derivative story problems that take advantage of our ability to maximize and minimize things. We spent the last couple sections learning about how to get maximum values, minimum values, global and local out of functions. So now we're going to make some story problems that are asking about maximum values or minimum values, and we're going to use calculus to solve those story problems. There's a little bit of build-up. Most of this is just going to be me doing examples at you. Before we start doing examples, I want to talk briefly about the structure of almost all of these problems. Almost all of these problems are going to involve two different relationships. There's a relationship that we want to maximize, and then there's going to be some sort of constraint that we need to adhere to in maximizing this. Because the constraint is what makes this like a doable problem. If you're looking at a problem like what's the biggest area you can enclose with a fence, like that's almost like a philosophical question, right? Like, the world? What does it mean to be enclosed by a fence on a scale that big? So you need to have a constraint. Like, you have a finite amount of fence. Now what's the largest area you can enclose? That's the kind of problem we're going to be doing. So the area that we're enclosing is going to be the relationship that we want to optimize. And then there's also going to be a constraint there that makes it into an actual optimizable problem. That's the amount of fence that we have. So that's going to be the two things that we're looking at. We're going to try and get a relationship between those things so that we can do calculus on it in a meaningful way. With that in mind, let's just get started. The quintessential optimization story problem involves a farmer, who we're going to call Kaide, and that farmer enclosing an area with a fence. To make this a little bit less boring, a little bit more interesting, we're going to say that she only needs to enclose 3 sides of her rectangle with a fence because this particular pasture has some river. So there's river up top, and we're going to enclose fence in a rectangle shape on 3 sides to make a pasture for grazing lands. And the question is, if she has 1,000 meters of, if Kaide has 1,000 meters of fence, what is the largest area she can enclose? This is the story problem. So, here's where the sort of two different relationships come into play that we're going to put together to create something that we can do calculus on. The thing we are trying to optimize is this area. We could say that this is a y value, this is an x value, that would be another y value. That gives us this relationship, area equals x times y. That's just the area of a rectangle. As it stands, this relationship is not something that we can optimize using Calc 1 because this is a multivariable expression. The area depends on both x and y together. That's going to make this annoying. We can't do it. But we do have this constraint. She has 1,000 meters of fence, so we need to use the constraint to transform this into something that is optimizable. If she's going to split 1,000 meters of fence between these three sides, then we have this relationship. X plus 2y equals 1,000. Which means x equals 1,000 minus 2y. Which means that this area, we squiggle this over here and plug it in for x, this area can now be expressed as 1,000 minus 2y times y, which can further be simplified into 1,000y minus 2y squared. And this is a relationship that we can optimize using Calc 1. This is a relationship between the length of one side of this rectangle and the area of the rectangle. We can do that. We can take a derivative of this without getting the product rule or multivariable nonsense involved, and that's the goal. So, we're just going to go right ahead and optimize this. If this is the area, optimizing it means the same thing that optimizing has meant for the last three sections. You take a derivative, you set the derivative equal to 0. Where the derivative equals 0 are going to give you maximums and minimums for this function. And from there you kind of just have to use common sense to like interpret what these numbers mean and which one is a maximum and which one's a minimum and whether or not that makes sense. So we need a derivative. The derivative of area is 1,000 minus 4y. And then when you set that equal to 0, you get 1,000 equals 4y, and y equals 250. Interpreting this back within the context of the problem, this means that y should be 250 meters, which would also mean that this is 250 meters. And then this x distance would be the leftover fence, which is 500 meters. Does this make sense as the maximum possible area for a rectangle like this? I think that it does. 250 times 500 seems like a really big area you can get out of 1,000 feet of fence. That would be something like 250 meters times 500 meters would give you something like 125,000 square meters, which is big. I think you'll find that it's bigger than the amount of area you get if you just cut this into 3 equal pieces and use the same length for all 3. One of the reasons I like this problem so much is because when you first read the problem, it's sort of intuitive to think that the correct answer should be a square. And the square is the correct answer when there's not a river involved. If you need to use fence for all 4 sides of this enclosure, then the square is the shape that maximizes the area. Well, a circle is the shape that maximizes the area. But the square is the rectangle, the rectangular shape that maximizes the area. But it changes when you get this river involved, because this side doesn't need fence. This side can be much longer, which I think is very interesting. So this function only has one critical point. We've sort of decided that it is the maximum. The reason it's not giving you other critical points is because the minimums for this situation would be 0 on the y and 1,000 on the x, which does not give you any area at all, or 0 on the x and 500 on each of the y's, and that also does not give you any area at all. So if you consider this to be a constrained problem, like y is in 0 to 500, these two are your minimums, this is your maximum. Our first optimization story problem. We're about 10 minutes in. I think I have time for another one in this video, and then we'll make a second video for the really weird one. Let's get started. Okay, here's the second story problem I want to talk about. This is a graph of the function y equals 8 minus 2x in the first quadrant. I want to pick a point on this graph, and I want to use this point to create a rectangle with the x and y axis. I want to know which point on this graph maximizes this area. We could get a long skinny rectangle if we put it close to the bottom. We can get a tall skinny rectangle if we put it close to the top. Somewhere in the middle there should be the point that maximizes this area, and I want to know what it is. So this problem is going to feel a lot like the other problem, where what we're maximizing is the area of a rectangle, x times y. We are maximizing this thing. The constraints are going to be a little different though. Whatever x value we choose, our y value is going to be dictated by this function. So I'm going to replace that here for our x, 8 minus 2x. So I'll get a equals 8x minus 2x squared, and this is now the function that I'm trying to optimize in terms of one variable. So I'm going to take a derivative to optimize it. That will give me 8 minus 4x. That's what I'll set to 0. I will get x equals 2. That would mean that y is 4. Seems pretty optimized. In hindsight, this is a lot more similar to the first question than I meant it to be. That's okay. It only took like 2 minutes. We have time for another one. Two positive numbers multiplied to 100. What is their minimum sum? So again, we see that there's sort of two different relationships happening here. There is the optimization relationship is a plus b. I want to minimize this, the sum of two numbers. The constraint, I'll say that this is the sum. Sum equals a plus b. This is what I want to minimize. The constraint is a times b equals 100. So I need to manipulate this constraint. I'll say that a equals 100 over b. I will substitute this in here so that I can create an optimization function that uses only one variable. So now I have the sum is 100 over b plus b, or perhaps it would be better to write this as 100b to the negative 1 plus b. this is now the equation I want to optimize as a function of one variable, so I can start taking derivatives. Sum prime equals negative 100b to the negative 2 plus 1. This is what I'm setting equal to 0. So I'm going to come up here to solve it. 1 equals 100 over b squared. If I do some manipulations, I can add this to both sides of the equation. That'll make it positive 100b to the negative 2, which is positive 100 over b squared. I can multiply both sides by b squared to get this, which should give me b equals 10. Which I think also means that a should be 10 if it's 100 over b. So, this hopefully is pretty intuitive. Hopefully when you wanted to minimize the sum of two numbers that multiplied by 100, you were thinking, I bet they're the same number. If you were thinking that, that's correct. But we can now prove that that is definitely the case using calculus. So that's pretty exciting. That's going to do it for this video. That's been 3 relatively straightforward examples of optimization problems using calculus to maximize or minimize something. The really good problem, my favorite optimization problem, that'll come in the second video, so stay tuned for that. But this one's over.